Hello, my name is Amos Peter, and you're welcome to another lecture in the series of our computer architecture lecture. And in this topic, we shall talk about word formats and the various word formats as it pertains the computer microprocessor. Generally, in the computer system, data can usually be stored in the form of zeros and ones. And suppose this is a storage device. It is possible for us to store either a 0 or a 1 in this memory location. And a group of 8 of such devices can store 8 bits of information. Now, this 8 bits of information gives us what we refer to as a byte. That is, 1 bit gives us 1 byte. Now, several bytes gives us what we refer to as a computer. It forms what we call one computer word. Now, conventionally, while 1 byte is composed of 8 bits of data, there's no generally acceptable number of bytes that forms a computer word. It's all dependent on the CPU architecture. That is how the architect or the company that produces such a microprocessor decides to design the system. So in other words, when we say several bytes forms a word. So for example, you could have a microprocessor that is 16-bit. It's a 16-bit system. You could have 32-bit machine. You could have 64-bit machine. In other words, a 16-bit machine actually makes use of 2 bytes as its word length or word size, while in the case of 32 makes use of 4 bytes. In the case of 64 make use of 8 bytes of data. Now in the next slide we shall see how the definition looks like of what a computer word is all about. Now in computer architecture, a word is a natural unit of data of a defined bit length which can be addressed and moved between storage medium and the computer processor. Now usually the defined bit length is a word. Of a word is equivalent to the width of the computer data bus, so that a word can be moved in a single operation from storage to a processor. And usually the word size of a computer is usually indicative of the memory size that such a microprocessor can access. For example, a system or a microprocessor that has a word size of 16 bits is capable of addressing 2 raised to the power of 16 bit memory location. And if you do the math, that will give you 65,536K. While in the case of a 32-bit system, it is capable of giving you 2 raised to the power of 32. And if you do the math, that will be a little over 4 gigabytes of memory location. So usually the computer or the microprocessor word actually comes in multiples of 8, 16, 32, 64. And this is because usually when you scale by a factor of 2, it is much more easier for you to divide and handle stuffs. So that is why the computer word size usually comes in these multiples. Now let's consider a 32-bit machine. In a 32-bit machine, the 32-bit machine is capable of handling, that is, one word in a 32-bit machine. One word is equivalent to 4 bytes. And in the case of this machine, suppose we picture the memory to be of this form. This is a memory location where we have rows of data in the form of what we refer to as the word. So each of these is actually a word. So if we have this is I plus 1, I plus 2, up to 4095, and here we have 32 bits. That is 4 byte, 4096. So this refers to the address of each memory location. Now let's put it side by side with another equivalent memory, but in this case using the concept of byte addressable memory. So we have this memory of the same size, where this is 32-bit, and then each of this memory is being splitted into bytes, and here we have J plus 1, we have J plus 2, we have J plus 3, we have J plus 4, here we have J plus 5, J plus 6, J plus 7, J plus 8, J plus 9, J plus 10, J plus 11. Now, if you look at this very particular memory critically, now each of these are actually addresses of each of the bytes. Now, by comparison, you can now see that on the left-hand side, the word address I corresponds to the first byte address here of J. Similarly, the word address of the second memory location on the left-hand side is I plus 1, while its equivalent on the right-hand side is J plus 4. The next on the left-hand side is I plus 2, while on the right-hand side is J plus 8. In other words, in the byte addressable scheme, for us to reach the address of each byte of, in the case of the byte addressable, to reach the next word location, we simply add the number of bytes that each of the word has to the preceding address, while in the case of the word addressable scheme, to reach the address of the next word, we simply increment the preceding word address with a value of 1. Now in this slide, suppose we want to address a particular memory size, and we are asked to find the number of bits required to address each of the word, and also the number of bits required to address each byte. How do we go about it? Now usually this is a fairly simple work to do, and basically we make use of the formula which says 2 raised to the power of n is greater than or equals to size And here in this case, size simply refers to the memory size. So for example, in the case of the first here, we have a memory location that has 4096 words, and each is 16-bit wide. In other words, 2 bytes wide. Now, what we are supposed to do is to solve a problem of this nature. For example, we have 2 raised to the power of n greater than or equals to 4096. And what we are required to do in this case is to solve this equation such that n, the value of n, is greater than or equals to 4096. And there are 2 approaches or ways you can solve this. You can either make use of the logarithm, natural logarithm to base 2, or you can use another simple method if you simply know your power of 2. Now, from this very particular equation, you will realize by inspection that 2 raised to the power of 12 will actually gives you exactly 4096. So in other words, n is equals to 12 will give you the number of bits required to address each word in this very particular memory. Now, in the case of the number of bits required to address each byte, all you need to do is just for you to have 4096 multiplied by the number of bytes you have. In the case of 16 bits, that gives you 2 bytes. And of course, this could be represented in this form. 4096 is 2 to the power of 12 multiplied by 2 to the power of 1. And of course, if you add the power, since they are of the same base, that gives you 13. So this simply means that for us to address each byte of this memory location, we require 13 bits of data to do that. Now, in the case of this 1024 memory location, a quick look at the same equation, which gives us 2 raised to the power of n is greater than or equals to 1024. By inspection, you can quickly find out that 2 raised to the power of 10 gives you 1024. So this implies that the number of bits required to address each word in this case is 10. While in the case of each byte, it means we are going to have 1024 multiplied by 4 bytes. That's by 4 bytes, which gives you 2 to the power of 10 multiplied by 2 to the power of 2. And if you add the powers, that gives you 12. So in this case, we have 12 bits are being required in order to address each of these byte location. Now, at this point, I would like to leave the remaining 2 to the student as just a homework. When you follow the previous procedure I've just outlined, it should be much more, very much easier for you to arrive at the correct answers to this simple problem. So I would like to call it a day at this point, and I hope that the information I have just passed in this lecture has been very, very informative, and I would like to thank you for viewing. And I also ask that you should be on the lookout for my subsequent videos in the series of lectures on computer architecture. Thank you very much. See you next time.